Great. First of all, I want to thank the organizer to give me this opportunity to present some of the, I think, exciting, weird, debatable results that I'm going to show in the next 20 minutes. I haven't really got a chance to show much of those, so I put all of them together. Hope I can fit all of them in 20 minutes. And the thing I'm going to talk about is all kind of in my opening slides, the Milky Way here, large Magellan Cloud or LMC here, some of the disrupting dwarfs, some of the ultra faint here. And I originally not planning to talk about streams, although I worked a lot on that, but I realized that every theorist is working on streams, so I should show some observational result on streams. So that's what I'm going to have, and I have an outline, try to keep up the kind of flow because I'm jumping around things. So my first half of the talk will be on why Milky Way satellites are elliptical triaxial. And again, I'm not trying to tell you how these things apply to the nature of dark matter understanding, but more I want the theorists to tell me whether any of those exciting observational results are interesting to you, and maybe you can tell me how to interpret the result. And for that part, I will mention the impact of LMC on the Milky Way's, LMC on the Milky Way satellites. And I'm gonna mention about some of the observational results on intact dwarf, disrupting dwarf, and disrupted dwarf. Again, the last one, basic stellar stream, that I will mention at the end if there's time. Okay, and I want you guys, the goal for me is I convince you, I attract you enough so you can tell me whether anything that I showed you today can tell us something about dark matter. Maybe I'll be here for another 2 weeks, so people who will be here can help me to answer that question. Okay, let's start from the first part. Why Milky Way galaxies are elliptical triaxial. Why I need to start the story with LMC. I will go through this very fast, so Robin has mentioned that yesterday already. So the idea that is, we know that LMC is coming in the past few giga-years and making this wake and the collective response in our Milky Way, and our Milky Way halo is not in dynamic equilibrium. And there's a lot of observational data to study the halo. For example, this shows the density map did by Charlie Conroy's group that showing the data, the density distribution of the stars at particular distance on the left and right. Again, if Milky Way is in dynamic equilibrium, we assume the density should be all close to the white color, but you see overdensity, underdensity, and that is because of the LMC perturbation. Similarly, in kinematic space, you see the velocity in galaxy and the rest also has some going one direction, some going in the other direction. Again, it's data here and a simulation here. So that's something already know. How the LMC info impacts the Milky Way's companion. So I'm going to show one example very quickly on streams. This is often Shenada stream, where we have now from the collaboration I'm in, a lot of the results I'm showing is from the S5 collaboration that I'm leading. So we have the full 60 data for over 200 member stars in this stream. And with that, we can model the stream to include the Milky Way mass and the shape and the LMC mass and shape. And in order to explain the data, we have to have LMC comes in, largely perturb the southern part of the stream and make this strong kind of weird torque. And from that, we find that either the Milky Way dark matter, the mass profile have to be triaxial, or we need to model the dynamical friction parameter to fit the data. So for more detail, I would encourage you to look at this paper. So yes, LMC come in, perturb the stellar streams in our Milky Way. That is something we learned. How about the satellite galaxies in our Milky Way? That's the next question I want to ask. So these are what we think are the intact dwarf galaxies, the galaxies in our satellite galaxy of Milky Way. So first is to ask what about the orbital parameters like the pericenter and apocenter. So this is the work led by Andrew Pace, and I'll mention this paper several times for the rest of my talk, where that Andrew has been taking all of the dwarf galaxies in our Milky Way and then try to compute the peri and apo with and without LMC. And we can see for about a third of the Milky Way satellites, this is about a third of all the Milky Way satellite galaxies we know, like a third of them has either a pericenter shift or a pericenter shift. So this is apo, this is peri. For more than 25% of its original. So LMC do make an impact on the pericenter or apocenter of the dwarf galaxy. Okay. So why I talk about all of these if my subtitle of the first session is dwarf galaxy, why dwarf galaxies are triaxial. So I need to touch one galaxy first to give that complete story, which is Antlia 2. So yesterday, Jorge talked about some of these dwarf galaxy lack of dark matter, one of ultra diffuse galaxy. I personally think Antlia 2 could be a good candidate in that category in our Milky Way. So Antlia 2 has almost the same size as LMC, but the surface brightness is way lower than that. So it is not discovered until 2019, after Gaia release, or 2018 or 2019 after Gaia release. It has current distance at 130 kiloparsec. The half-light radius of it is 4 kpc. So it is definitely fulfill the ultra-diffuse galaxy definition. Its pericenter is at 40 kiloparsec, so not that close. Its apocenter is at 140 kiloparsec. And this is like how it looks like on sky. So it's highly elongated, and this semi-major axis basically is 4 kiloparsec. From the work that the Alex G led within the S5 data, we show that the velocity of the stars in this galaxy as a function of semi-major axis, so this direction, show a very clear velocity gradient. So we confirm that the galaxy is under tidal stripping, and although it has a quite large pericenter, and the puffiness here we see can be explained by a galaxy under tidal stripping. But the puzzle is, and this is where the LMC connects to, the puzzle is, if this elongation we are seeing is tidal debris around a dwarf galaxy, then we expect the semi-major axis, which is this black line, should match with the motion of the galaxy, which is the purple line. But they are not. So what is going on? And until later we realized we have to consider the LMC-ing. Think of a way that when we compute the motion, we need to consider the motion of the sun to correct for the reflex motion of the sun. Because of the inflow of the LMC, we need to correct for that kick of the whole Milky Way disk with response to the inflow of the LMC. So if we consider that, then that's a very nice result. Antlia 2, we know it's under tidal stripping. It has a high elongation, and that elongation, the morphology elongation, the semi-major axis, matches with the motion after correcting the inflow of LMC. Great. Now I come to my question, and this is what I want to ask for my first part of my talk, is dark matter, dwarf galaxy we are seeing in our Milky Way, a lot of them show elongations, triaxialities. When I was a first-year graduate student or second year starting to work in the field, I asked why these galaxies are elongated. People say because dark matter are form triaxial shape, and that's why they live in these galaxies, so they are elongated. We definitely see some of these elongated dwarf galaxies in the field too. But now my question is, these dwarf galaxies in our Milky Way, they are elongated. They are as a consequence of dark matter or tides. And I hope using next 2 to 3 minutes to convince you or to make you think about this question. So Antlia 2, I have talked about. We see it's highly elongated, and the motion and the morphology, the semi-major axis align well after considering the LMC. Carina is another example. Here, this is again taken from Andrew's paper that we did 2 years ago. The arrow here in orange shows the motion of the galaxy, and the red shows the direction to the galactic center. So for example, Carina is elongated. We find that the elongation morphology matches with the motion, which is the orange here. Hercules, another one, it is elongated, and again, the elongation direction matches with the motion. And we made this kind of some plot where you're seeing the x-axis is delta theta. The delta theta is basically these two angles, right? One angle is the mu angle is a proper motion angle, so it's this purple line. And the delta x, or theta xy is this black line. So again, if they are 0, that means the morphology and the motion are aligned. If it's 90, then it's perpendicular. And the y-axis here you're seeing is the ellipticity of how elongated this thing is. So this is what we are seeing for all of the galaxies in our Milky Way that has good proper motion measurement, so we can put on this plot. So for anything that with ellipticity larger than 0.4, so some of these systems I'm showing here, we found that there's definitely more alignment than disalignment. There's definitely a preferential. And I asked this question for this galaxy, Rectangular 2, when it was discovered. Rectangular is famous for many things because of dark matter annihilation, our process. And I said, oh, this galaxy is hugely elongated. Why is there? And you will think, okay, the proper motion of the galaxy is going this direction. The elongation is this direction. That's why you can see the delta theta here is 60 degrees. It's not aligned. So it's not like the other ones that I'm showing. However, going back what I introduced the story as the LMC info impact, we did this particle spray model with GalPy for this particular galaxy. If we don't consider LMC, the particle goes this direction, which matches with the motion of the galaxy. But if we consider LMC, the particle spray goes this direction. So actually, if we consider the LMC info, that the point here could move also close to zero. This is again telling us all of the high elongated dwarf galaxies in our Milky Way, their morphology elongation matches with their orbital motion. Why? I don't know the answer. It's the first question I want to give to you, and great, I only used 10 minutes on this topic. So the conclusion I have is all highly elongated Milky Way satellite galaxies has the ellipticity aligned with their orbital motion. But that's weird. People tell me these galaxies are triaxial because they form triaxial, but then why they matches with the motion? So are dwarf galaxies elliptical because of tides? Were they born in spherical and then get elliptical, or were they born in elliptical and then aligned due to torque? There's a lot of work from the some of the theory work or the observational work show that it should be the last one. But the aligned due to torque should make the semi-major axis point towards the galaxy center rather than point towards the orbital motion. So this is the first question I want to throw into the theorists, and I would like to ask you guys. As you can see, the last part, we didn't really write a paper because I don't know how to explain these. So hopefully I can actually work on a paper in the next few weeks while I'm here. Okay, I wanted to throw in one thing that argument that people think these things are not under tidal stripping or influenced by tides using this plot. So what you are seeing here is all the Milky Way satellite galaxies. The x-axis is the pericenter of all of these galaxies. The y-axis showing you the density, the average density of these galaxies within the half-light radius, calculated from kinematics. And this line shows you at the pericenter what is the average density of the Milky Way halo times 2. So if things above this or well above this line, that means like the density of the dwarf galaxy, the dark matter density of the dwarf galaxy is way higher than the Milky Way's halo density at that location. So these things should be all intact. So that's why we think these things shouldn't influenced by tides much, at least within the half-light radii. But the fact is these are the ones that we are seeing this correlation between the morphological kind of elongation and the motion direction. So this is really a puzzle to me. Okay, now I'm moving on to my next part of the talk that I want to show you guys some of the observational results on 3 different categories of dwarf galaxies. And I'll go through very quick. The first part is on the intact dwarf galaxy. If you still think they are intact, maybe not based on my first part of the talk. Okay, so this is just very quickly showing you one result coming out recently, or will come out hopefully soon, is on Bootes 1, which is one of the most luminous ultra-faint dwarf galaxy. And we all have known that there are a lot of study on the density profile on Milky Way dwarf galaxies, but a lot is at the high mass end for the classical dwarf, which we think have impacted by the stellar feedbacks or to make the density profile a bit flattened. So this is for the Bootes 1, which is the most bright, one of the brightest ultrafaint. So hopefully we have less stellar feedback for the density profile. So this is a work done by Kohei Hayashi using the data that collected from VLT led by one of my former undergraduates. So you can see that with about 50 stars mostly within 1 half-light radii, this is the constraint for the density profile. But over the past year, we have been adding more data from the S5 collaboration. So this is work like by my current postdoc. So we have been getting member stars up to 5 half-light radii. So with a much larger data sample and also much larger coverage on the sky, we were able to get a much better density profile measurement. So hopefully this work is going to get out very soon. Okay, so this is just one example of the intact dwarf galaxy. The next part I want to talk about this disrupting dwarf galaxy. So Antillia 2, what I would say is one of those. And there are not just Antillia 2. So I highlight 5 of them here. Tucana 3, Bootes 3, Sagittarius, everyone know, Crater 2 and Antillia 2. So Antillia 2 I've talked about earlier, that we show that there's a velocity gradient there. And these are the ones that you can see, they all, except for Bootes 3, they're all below these dashed lines. So their density, based on the kinematic calculation, they are below the average density of the Milky Way halo at that position of the pericenter. Also, you can see from the pericenter versus half-light radii, the size of the galaxy, these 5 stands out. They are much larger compared to the rest of the galaxies and at the same pericenter. So those 5 are under tidal stripping, but they still have the progenitor scene. Okay, let me go through a few of the latest results on each of those. I think I will not talk about the Sagittarius Antillia 2. Everyone knows Sagittarius pretty well. I mentioned Antillia 2 a little bit earlier. So first, I want to say Bootes 3. So Bootes 3 was above this line because people measured a velocity dispersion of 10 kilometers per second. Our latest work, which hopefully will publish soon because the undergraduate student graduated, so I need to take over and actually finish the paper. But the conclusion of this work is, instead of it's a 10 kilometers per second, we find the dwarf galaxy has less than 1 kilometer per second velocity dispersion. So it is definitely dark matter deficient, and it is under tidal stripping. That's a recent result on the Bootes 3 here. It also matches with this picture here. The next one is Tucana 3. That is the first disrupting dwarf I worked on when I was a postdoc. And here's the result showing from the discovery, a dwarf galaxy there with a tidal stripping tails. And then we find the member stars from spectroscope follow-up with a gradient. And then we fit the orbit with a pericenter of 1 kiloparsec and an apocenter about something 50 to 60. So think about it. It's a dwarf galaxy, get as close to the Milky Way center as 1 kiloparsec. I would be shocked that actually no theorist has get interested working on it, given it is 6 years old. So I want to re-emphasize it. Okay. Okay, then very quickly on Crater 2, that's another one people also think it's a puffy galaxy that we think is under tidal stripping. So finally, with the spectroscope follow-up work, we identify member stars along the motion of the galaxy. So we definitely see member stars from the spectroscope follow-up. And the work did by Kobe et al. Also show that our Lyrae stars that are members and show very clear velocity a distance gradient here and the velocity gradient here that matches our M-body simulation. Okay, so these are the galaxies under tidal stripping. And again, this is connected to the dark matter. So I should tell you how these things could be used to constrain dark matter, but I'm really observer. I want to throw you that there's so many cool results. So you can tell me whether I should continue working on it or what kind of proposal we should write. But I did a bit of literature reading or talking to Highball and then find, okay, there are some things that you can do with these disrupting dwarf galaxies to probe the nature of dark matter. So I think for example, the unusual large size of these galaxies I showed, right? These galaxies are very unusually large and the velocity dispersion is very low, meaning their dark matter is very low. Cannot really explain by CDM, claimed by a lot of groups. And some people think it's MOND can explain it. Some people think SIDM can explain it. So this is what Highball and Xinyu's work that who both are in the audience, so you guys should check with them. But the idea is they don't think CDM explain the current size and velocity dispersion, but SDM can. And this is another work done by Rafael Irani, way before Antillia 2 Crater 2 were discovered. And they claim, if I understand correctly, they think the dispersion, velocity dispersion of the tail versus dispersion of the core is the ratio of that is cusp versus core dependent. If it's cusp, then it should be very similar. But if it's core, then the stream should be much hotter than the tail. So those are the predictions. So I think we are really at the era we can make those comparisons using the observational data we have. Okay, very quickly for the last part, the disrupting dwarf galaxies or the stellar stream. It was not originally in my plan to talk about, but I just want to tell people there are a lot of scientific results on that. Ray talked about globular cluster stream. I believe Sarah will also talk about globular cluster stream. So I want to emphasize a little bit on dwarf galaxy stream. So the stellar stream originated from dwarf galaxy. Okay, 1 minute is good enough. And so this is some work that I did 2 years ago for what we observed in S5 for a dozen of stream. And these are 12 streams without any progenitor identified at a distance between 10 to 50 kiloparsec. So it's relatively farther compared to a lot of newly discovered streams from Gaia. And 6 of these streams are dwarf galaxy stream. And I'm just going to show one one or maybe two slides about the result on this. So we have been getting a lot of interesting results, but I don't know if it's from dark matter-wise or galaxy evolution-wise, it's interesting. So that's why I want to throw it to the audience. For example, among these 6 dwarf galaxy streams, we found the velocity dispersion increases as the pericenter goes down. And that's what we see. But I don't know if there's something meaningful. Maybe because the stream got closer, so that's why it get heat up more. And there are a lot of other findings. I don't have time to show slide per finding, so I'm just going to list the bullet point, but I do have slide for each of them if you ask me in the question. So first finding, the observations show fewer massive stellar streams than fire predicts. The second finding, the observations show smaller pericenter apocenter than fire predicts. The third finding, the stream have higher orbital eccentricity than the intact satellite galaxy. The fourth finding, the stream prefer prograde more than retrograde from the observation. Okay, and the last promise, the last slide, oh no, not me, is this is not really part of the dwarf galaxy stream, but everyone talk about GD1, which is great. I love GD1, but I just want to let people know there are other globular cluster streams. We see spur, gap, and we can constrain them with some halo. So check out these papers. There are more than GD1 that is interesting for dark matter subhalo perturbation study. Okay, so with that, I will conclude my talk, and I wanted to mainly tell you there's a lot of observational results here, and please talk to me. Hopefully, some of those will be useful for your crazy idea or crazy dark matter model fitting. And with that, I'll end my talk with a group of people who did all the awesome work, and we have like over a dozen papers in that link if you want to check out. Thank you.
Thank you.